In this lesson, we're going to talk about all, some, or no solutions. Up to this point, we've been talking about equations that have one solution. So there's one value that we can substitute in for our variable that makes both sides of the equation true. But today, I want you to start thinking about how many solutions can an equation have? We're going to start off with our warm-up doing which one doesn't belong. So I'm going to give you a set of 4 equations, and I want you to pick one out that looks different. One that you feel like does not belong with the rest, but I want you to justify why you've chosen that one. So right now we should be in page 49 in our student workbook, lesson 7. So go ahead and take a couple minutes to read through 7.1, pick the one that you're going to select that doesn't belong, and add your reasoning. Let's take a look at the top left equation. So what makes this one different? If you said the fact that it has addition, you're correct. So this one has addition. It's the only one with addition. But I want us to dig a little bit deeper and look at some other components of this equation. So do we have a true statement? Absolutely we do, because 12 absolutely equals 12. Let's look at the top right. So here, this is the only one with multiplication. Now, one thing that I want to point out about this top row is we're looking at commutative property. So we're looking at commutative property of addition on the left and commutative property of multiplication on the right. So what does that mean? I can add numbers in any direction and the sum is going to be the same. I can multiply numbers in any direction and guess what? The product is going to be the same. So what's my product here on the right? 35 definitely does equal 35. So again, we have another true statement. Let's take a look at the bottom left. So when I look at this one thing that I notice is there is only one digit to the left of the equation, or the left of the equal sign, whereas all the rest of them have 2 terms on the left and 2 terms on the right, right? So we don't see that here with the bottom left, but we still do have a true statement. So I have 2 equals 2, because 7 minus 5 is 2. So again, the thing that makes this one stand out is there is only one term on the left. All right, so now let's look at the last one. So you might be looking at this and saying commutative property of subtraction. And if that's what you're thinking, not quite. There isn't a commutative property of subtraction. Why? Because when you change the order of the numbers when you're subtracting, the value also changes. So that difference changes. 5 minus 7 is negative 2. 7 minus 5 is positive 2. Are these two values equal to one another? No. Okay, so what is something about this particular equation that doesn't belong? It's a false statement. So it is not true. All right, let's keep moving. So again, today we're thinking about solutions. We're going to start looking at different equations and reasoning about the type of solution or the number of solutions that we will have. So here we're looking at 2t plus 5 equals 2t plus 5. So what are some things that you notice? Do you notice that the same thing on the left is also on the right? So what is a value of t that would make this equation true? Let's try a couple values. Let's say t equals 0. When t equals 0, I can substitute that in on both sides, right? Wherever I see t. 2 times 0 is 0. So I'm going to have 5 equals 5, which is correct. What if I tried another value for t? Let's say 10. So 2 times 10 plus 5 and 2 times 10 plus 5 again. Well, 2 times 10 is 20 and 20 plus 5 is 25. So 25 definitely does equal 25. So now I've tried 2 different values for t and both of them worked. Why do you think that is? Is it because the expressions on either side of the equal sign are the same? Yes, that is why that works. So let's look at another one. So here we have n plus 5 and n plus 7. What do you notice about this equation? Hopefully you see that there are n's on both sides, but in this case, we're adding different amounts. So on the left side, we're adding 5, and on the right, we're adding 7. Do you think that makes a difference in how many solutions we can have? Okay, Let's try it out. So if n equals 0, that would be 0 plus 5 and 0 plus 7. Well, 0 plus 5 is 5 and 0 plus 7 is 7. Are those two values equivalent? No, they're not. What if I said n was 12? So that means I have 12 plus 5 and 12 plus 7. That would be 17 equals 19. Is that true? No, it's not. So when we have expressions that are not the same on both sides of the equal sign, do you think that makes a difference in the number of solutions that we have? Probably so. Because notice here that we only have one n. There's one n on both sides, right? So let me just show you something. I want you guys to see what happens if we were to solve this equation. So let's say I subtract 5 from both sides. So now I have n is equal to n plus 2, right? So then I'm going to combine my n's. So I'm going to subtract n from both sides. So now I have 0 equals 2. Well, 0 does not equal 2. So notice how I'm not going to be able to find a value of n that is going to create those balanced sides. So this one would be no solution. Now we're going to look at some different equations in a minute so that we can kind of come up with a strategy or come up with a thought process around what equations should look like when we have all solutions and no solutions. So far we've talked about two kinds of equations. So far today. Now, prior to today, we talked about having one solution. So x equals 3 or x equals 5. Now, today we have introduced a new idea, and that is having many solutions. So when I have that same expression on both sides of that equal sign, I have many solutions. It's a many solution situation. Okay. Now, on the contrary, when we're looking at expressions that are not equivalent on both sides, okay? So now we have some number that we're adding completely different numbers to. So it's the same number, right? It's the same number, but I'm adding a 5 on this side and a 7 on this side. There's never going to be a chance. There's never going to be a situation where those balances are going to be the same. Okay, I can't take the same number, add two different numbers to it, and expect to get the same sum. It's not going to work. It's not going to work. Okay, but let's keep digging a little bit deeper. Okay, so now what I want us to do is turn to page 50 in our student workbooks. We're going to look at about 8 different equations and start categorizing. So I want us to categorize or sort based off of all solutions or all values or no values. So you're going to take a few minutes to begin working on page 50 right there at the top. And I want you to categorize or sort those equations. I want you to label them with whether or not all values would work or whether no values would work. So let's go ahead and start looking at our equations. So I'm going to number them just to make it easier for us to have our conversation. And we're going to start by looking at number 1. So number 1 just says 1n equals 1n. And that makes sense, right? It makes sense that n, whatever it is, would equal itself. So this one is going to be all values because no matter what number we substitute in for n, it's always going to equal itself. Whether it's 0, 1,000, -2, 1/2, all of those numbers are equal to themselves, right? So that one is always going to be true. Let's look at number 2. On the left side, we have 2t plus 6. And then on the right side, we have 2 times a quantity, t plus 3. So let's think about this. Is this going to be an all situation or a none situation? Well, let's see if we distribute what things could look like. So I'm just going to rewrite my equation here. And when I distribute that 2 inside the parentheses, I'm going to get 2t plus 6. Well, here we are again with 2 expressions that are the same. So no matter what value I substitute for t, both sides are going to always be the same. Whether it be -1 or 1,000, the value on both sides is going to be the same because what we have on both sides is exactly the same. So this one again would be all values. Let's look at number 3. So I'm hoping that you notice something with number 3. On the right side, we have 3n plus 1, but on the left side, we have 3 multiplied by a quantity in parentheses. Now, whenever I distribute that 3, I'm no longer going to have a 1 on both sides, right? Now I'm going to have 3n plus 3 equals 3n plus 1. Well, this is the same variable term, right? But on one side, I'm adding 3 to it, and the other side, I'm adding 1 to it. Is there ever going to be a situation where those balances are going to be the same? Where those values are going to be the same? No. So this would be no value. Okay, so there's no values for n that would make this equation true. Okay, let's look at number 4. So on the right, we see we have 5d. On the left, we see we have 1/4 multiplied again by a quantity. So already I notice that I have a constant inside my parentheses. So that's standing out to me already, okay? That's standing out to me already because whatever I end up with when I distribute this 1/4, I'm going to be adding something to my variable term. So let's just see what we got. So 1/4 times 20 is the same thing as 20 divided by 4. What's 20 divided by 4? Well, that's 5d. 1/4 of 4 is 1. So again, we got the same variable term on both sides, but we're adding completely different values. On one side, I'm adding 1, and on the other side, I'm not adding anything. So is there ever going to be an instance where this is going to balance? No. So this would be no values. There is no value for D that would ever give us a true statement. Let's look at number 5. So here I have some like terms that I can combine. 5 minus 9 is -4. -10 plus 6 is also -4. So what do you see? Same expression on both sides, which means all values would work. Okay. Now let's look at 6. I notice I have the same variable term. I only have 1x on both sides, but I'm adding 1/2 on the left and 1/3 on the right. Is there ever a situation where me adding 1/2 and 1/3 is going to give me the same amount? So that's going to be no values. Number 7. So here I have a -6 times -3. And then on this side, I have 2 times 9. Well, let's remember our integer rules. When I multiply 2 negatives, what do I get? A positive. So that's going to end up being 18y. 2 times 9 is also 18, and I multiply that times my y. Well, this is a true statement. I have the same thing on both sides. I got 18y on both sides, okay? So when those expressions are equivalent, that is an all values situation. Now, last one, we notice that we got a v term on both sides. But on the left, we're adding 2, and on the right, we're subtracting 2. So again, we're starting with the same number, but we're doing 2 different actions, doing 2 different things to it. Is there going to be a situation where it's going to be balanced? No. So this one is going to be no values. What are the different ways to write the other side of the equation so that it's true for all values of u? Well, we've already discussed that if we want the equation to be true for all values, then we need to have equivalent expressions on both sides. So what can we do to create equivalent expressions on both sides? So what I'm going to do is I'm just going to distribute, okay? So that's going to give me a 6u minus 12 plus 2. Now, I could write it this way because this is an equivalent expression, right? I could also write it as 6u minus 10. Again, as long as I have equivalent expressions on both sides of the equal sign, then I'm going to have an all values situation. Now, what about if I want to do no values, okay? I don't want any values to be true. So what could I do here? So I could do, so now on the previous page, we had 6u minus 10. So what if I did 6u minus 14? Okay. What if I also did 6u plus 4? What are we noticing? So what I'm going to show you, let's go ahead and distribute because I want you to see both sides. So we got 6u minus 10. What are we noticing here? So let's just work with this one. I'm going to add 10 to both sides. So now I have 6u is equal to 6u plus 14. Then I'm going to subtract 6u from both sides. What are we going to end up having? What are we going to end up having? 0 equals 14, which is not a true statement. So notice here that when the coefficient is the same on both sides, right? When the coefficient is the same, but what we're doing to that variable term is different, that's when we have a no value situation. Let's continue to work through this and see if we can really start to understand what it looks like and what it doesn't look like to have all solutions and no solutions. So what's the equation? So for this part, we're going to be on pages 50 and 51. We're going to be filling in the blank for the equations to first create an all solution situation, and then next to create a situation where there are no values that we could substitute that could make it true. So I want you to go ahead and take a few minutes to go ahead and fill in the blank. And I want you to think about, what do your answers have in common and what strategy did you use to figure out what the answer had to be? All right, so let's look at the first one. So what do we notice here? We want to fill in the blank. We notice that on the left, we have 3x plus 6. And then on the right, if we want them to be equivalent expressions, we need something inside that parentheses that when we multiply it by 3 would give us 6, right? So what's that? That's going to be 2. So now we'll have 3x plus 6 is equal to 3x plus 6. Equivalent expressions, meaning no matter what the value of x is going to be, it's going to work. Let's try one. Let's try 2. So I'm going to substitute my 2. 3 times 2 is 6. And then 6 plus 6 is 12. Does 12 equal 12? All day, every day. All day, every day. So notice what we have here. We have the exact same thing on both sides. Doesn't it make sense that no matter what we would substitute in, the equation is always going to be true? I hope so. Let's look at the next one. So here we have x minus 2 on the left. Again, we want to create equivalent expressions. So what do you think should go in the parentheses? It's going to have to be a number that would allow us to get what? Negative 2, right? Because that's the part that's missing. So I'm going to substitute in a 2. I'm going to draw a little line here so we can separate our work. So now watch this. I'm going to distribute this negative, okay? So although we only see the negative sign, that is the equivalent of a negative 1. So negative 1 times 2, negative 2. Negative 1 times negative x, positive x. So on the left, I have x minus 2, and on the right, I have negative 2 plus x. So I know what you might be thinking. This doesn't look right. It doesn't look the same. Well, let's compare our terms. We have an x term on the left and an x term on the right. We have negative 2 on the left and negative 2 on the right. Are they not the same? Yes, they are. So since, again, we have the same expression on both sides, this is going to be an all values situation. Let's look at the last one. So on the left, we got a fraction. And we need to figure out what is going to go in this blank that would allow us to have equivalent expressions. So how can I do this? Well, I'm going to think about, if I simplify that left side, what should it look like? They've already simplified the negative 10 and 5. I just need to simplify the 15x and 5. So that would give me a 3x. So now when I simplify, I got 3x minus 2 is equal to 3x minus 2. So again, no matter what value I substitute, I'm going to get the same thing on both sides. Every single time, okay? So what did our strategies, what strategy did we use, and what did all of these answers have in common? Okay, so what's something that the answers had in common? Well, one, we had equivalent expressions on both sides. What strategy did we use? Well, We simplified, in some cases, we simplified one side to match the other one, right? So either we distributed or we divided or we multiplied. We did something with that left side. We looked what was on the left side and allowed that to help us create that equivalent expression on the right. Now, we're going to use these same three equations, but this time we're going to look for an opportunity to create no values, okay? We want no solutions this time, okay? So there's going to be no value of x that can make this equation true. So now I just want to remind you of what we did the first time. So we had 3x plus 6 is equal to 3x plus 6, right? Because we put a 2 in there. On the other one, we had x minus 2 is equal to negative 2 plus x, because we put a 2 in there. And on the other one, we had 3x minus 2 is equal to 3x minus 2. So again, notice we had the same thing on both sides. So now, for number 1, what could we possibly insert in our blank so that we don't have equivalent expressions on both sides? Let's try a 5. If I insert a 5, I now have 3x plus 6 is equal to 3x plus 15. Is this going to be an all solution situation, or is it going to be a no solution situation? Notice how my variable term, I have it on both sides, right? Got my variable term on both sides. But the difference is I'm adding two different numbers, okay? Remember we said earlier, if you take the same number and you add it to two different numbers, you're never going to come up with the same sum, okay? So let's just, for a moment, let's try one. Let's do 1. X is equal to 1. So hopefully you already see what we have here. So 3 times 1 is 3, plus 6 is 9. 3 times 1 again is 3, plus 15 is 18. Is 9 and 18 equivalent? No, it's not. Nope, it's not. Well, let's look at if we were to solve it, what it looks like. So I have 3x plus 6 is equal to 3x plus 15. So I'm going to subtract 6 from both sides. When I do that, I'll get 3x is equal to 3x plus 9. When I subtract 3x from both sides, I now have 0 is equal to 9. Well, is it? Is 0 equal to 9? No, it's not. So again, we figured out that when we substituted 1 in, okay, we did not get equivalent values. Then we solved it for x, and we see that there is not a true statement here. So there is not an x value that we could use to substitute into this equation that could make it true, right? So we chose 5 to put in our parentheses, okay? That's what we chose. The reason why we chose 5 is because we wanted to create a situation where the expressions would not be the same on both sides, okay? So now, what could we do for the second one? Let me draw my line so we can separate our work. What could we do for the second one? So let's try x minus 2 is equal to, let's say we substitute in, let's try 4. So now I have negative 4 plus x. Again, same x term on both sides, but I am adding different numbers, okay? I'm adding different numbers. So let's just substitute and see what we got. So I'm going to try, let's do 0. So I'm going to do 0 minus 2 is equal to negative 4 plus 0. So now I have a negative 2 is equal to negative 4. Is that true? It's not. So now let's do like we did in the previous one. Let's just solve the equation. So I have x minus 2 is equal to negative 4, and that's going to be plus x, okay? So then I'm going to go ahead and add 4 to both sides. That's going to be x plus 2 is equal to x. Then I have to subtract x from both sides. So now I have 2 is equal to 0. Well, does 2 equal 0? No, it doesn't. So again, we started off by substituting a value in, and then we actually solved the equation. And in either case, we did not have a true statement. We didn't have a statement that made sense. So what again do we notice? When we have those expressions that are not equal on both sides, we can have a situation where there are no values. Now, we have to be very careful about that though, because it's not going to necessarily be in every single situation where both sides don't match. Okay. Now, and we're getting ready to see this with the other side. Okay. So I want you to pay attention to the variable term. What do we need to be true about the variable term? We want to have the same coefficient with the same sign, right? Now, if we got the same coefficient with the same sign and we're adding or subtracting different numbers, that's when we know there's going to be no values, okay? There's going to be no values. So let's look at what we have for the last one. So we already remember when an all solution situation, we had 3x minus 2 equals 3x minus 2. So now, what could we substitute in here? So this is what I'm going to substitute. I'm going to substitute in a 3 times x. I'm going to put parentheses in here, okay? So I know that on this side, I have 3x minus 2. But then on this side, I'm going to have a 3x minus 6. So notice I have the same coefficient, right? Same variable, but I am subtracting completely different numbers from either side. So in this case, it's going to be a no solution situation. Well, is there something else that I could put here? Is there something else other than what I put? Yeah, there are other things. But the main thing is, if we have the same variable term on both sides, if I got a 3x on the left and a 3x on the right, but I'm adding or subtracting two different numbers, in that situation, that's where it's going to be no values of x will work, or no values for the variable will work, or no solution, okay? Now, how do we compare what we did previously to what we're doing now? Well, there were very specific values that we had to insert when we wanted to make all values true. Very specific values, because we had to have the exact same expression. Well, here, because we don't have to have the exact same expression, the only thing that we are restricted by is making sure the variable terms are the same and that we're either adding or subtracting two different things on either side. So what are some ways to determine how many solutions there were to the equations we solved today? So we can test different values for the variable, which is what we did. We can apply moves to generate equivalent equations, which is also what we did. We distributed, we divided, right? We can examine the structure of the equation. So look for those equivalent expressions, or look for that same variable term, but adding or subtracting a completely different number. So what I want you guys to do now is I want you to write a letter to someone who's going to be taking the class next year. And I want you to write about what they should look for when trying to determine how many solutions an equation has. I want you to use examples and share any struggles that you had during today's lesson, along with strategies that you prefer for finding the number of solutions. So today's goal was for us to be able to determine an equation, whether an equation has no solution, one solution, or infinitely many solutions. And we've reached the end, y'all. So what I want you to do now, check those notes, ask questions on the discussion board, go take that cool down.